When we think about computers, we usually think in black and white, true or false, 1 or 0. But that's not how the real world works, is it? Our world is messy. It's full of gray areas, hunches, and a whole lot of maybes. So the huge question is, how do you teach a machine, something that loves certainty, to navigate a world that has almost none of it? Well, today we're going to dive in and see exactly how that's done.
And this, right here, is the heart of the matter. This is the question we're going to unpack. It's not about an AI knowing everything for sure, because that's impossible. It's about how it makes the smartest possible guess with the clues it has. It's a skill we humans use constantly, and for an AI to be genuinely useful, it has to get really, really good at it.
So first things first, we have to accept a simple truth. The world an AI works in is not some clean, predictable chessboard. It's chaotic, it's unpredictable, and you almost never have all the pieces of the puzzle. For a machine that's built on logic, this kind of ambiguity is a massive challenge.
And look, this isn't just some abstract philosophical problem. Think about it. A self-driving car will never have a perfect map of every other car and pedestrian. A doctor can't be 100% sure about a diagnosis from just one lab result. This is the reality for almost every complex AI system out there. An AI just can't know things for certain, so it needs a way to talk about how likely things are.
And it turns out we have a language for that. It's the language of probability. Now don't let the math scare you. This isn't just about rolling dice or flipping coins. It is a seriously powerful toolkit that lets an AI put a number on its beliefs, and then, crucially, update those beliefs when it gets new evidence.
It all boils down to this super simple scale. Every possible thing that could happen gets a score between 0 and 1. 0 means absolutely no way. It's impossible. 1 means it is a stone-cold guaranteed certainty. And of course, pretty much all of real life happens somewhere in that fuzzy space in between.
Okay, now this is where the magic really starts. This concept is called conditional probability. Yeah, the notation looks a little intense, but the idea behind it is incredibly simple. It just asks, what's the probability of A, given that we already know B is true? This is the fundamental mechanic for how an AI learns from new data and gets smarter over time.
And this comparison just makes it crystal clear. Asking what's the chance of rain is one thing, but asking what's the chance of rain given that the sky is full of dark clouds, well, that's a much more intelligent question, right? That little word given is where all the reasoning power comes from. It's how an AI connects the dots.
So you might be wondering, how does an AI juggle all these different connected maybes at once? It can't just have a giant list of probabilities. It needs a map. It needs a way to see how one event influences another. And for that, we use something called a Bayesian network. Think of it as a blueprint for uncertainty. All it is really is a flowchart from maybes. Each bubble, or what we call a node, is just a variable we care about, like whether it's raining. And the arrows simply show what influences what. It's a surprisingly simple visual way to organize really complex, uncertain knowledge.
You know what? Let's just build one right now. It's way easier than it sounds. Imagine you've got a really important appointment and you have to take the train. The first thing we can think about is the weather. So let's make a node for rain. In our little model, nothing causes the rain, it just happens. So it's our starting point.
Okay, step 2. Let's add another factor, track maintenance. Now, common sense tells us that they're probably less likely to be working on the tracks if there's a heavy downpour. So we draw an arrow from our rain node to a new maintenance node. The chance of maintenance is now conditional on the rain. See how that works?
Now, what about the train itself? Well, a delayed train could be caused by heavy rain directly, or it could be caused by that track maintenance. So the train node is influenced by both. We draw arrows from both rain and maintenance to our new train node. Things are starting to get connected.
And here's the finish line, making your appointment. This depends directly on whether the train is on time or delayed. Now, here's a key point. We don't need to draw arrows from rain or maintenance directly to the appointment. Why? Because the train status already accounts for their influence. The effect flows through the network from one node to the next.
So what's actually hiding behind these arrows? It's not magic, it's just simple tables full of numbers. For every node, the AI stores something like this. This one says, hey, if the train is on time, there's a 90% chance you'll make the appointment. But if it's delayed, that drops to 60%. This is how the AI actually quantifies all those relationships we just drew.
Okay, that's the theory.
It's a cool diagram, it makes sense, but how do we actually build one? Well, the really awesome part is we can take that exact diagram and turn it into real working code. Let's see how a developer would actually do this using Python.
All right, first things first. We have to define that starting node, rain. So in the code, we create a node and we feed it what's called a discrete distribution. That's just the fancy way of saying we're giving it the starting odds, a 70% chance of no rain, 20% for light rain, and a 10% chance for heavy rain. This is our baseline belief before we know anything else.
Next up, we have to code the dependency. Here, we're creating the maintenance node. And notice the key part, conditional probability table. This is where we lay out the rules. See that first line? It tells the model, if the state of rain is none, then there's a 40% chance the maintenance state will be yes. We're literally spelling out the cause and effect relationship in code.
So now we have our nodes, our bubbles. We just need to connect them. And that's exactly what this code does. Remember the arrows we drew on the diagram? Each model.addEdge line is literally us drawing one of those arrows in code. We're telling the program precisely how information and influence should flow through our network.
And here it is, the moment of truth. This is the payoff for all our work. We can now give the AI a piece of solid evidence. We tell it, hey, I know one thing for sure, the train is delayed. Then we just ask the model to predict the probabilities of everything else based on that single new fact.
And boom, look at this output. Just by knowing the train is delayed, the AI has completely updated its worldview. It now thinks there's a higher chance of heavy rain than before. And most importantly, it's calculated a 60% chance we'll still make our appointment and a 40% chance we'll miss it. It reasoned backwards from an effect to figure out the most likely causes. That's just so cool.
So, what's the big picture here? What this all means is that by teaching an AI to embrace the maybe, to deal with uncertainty, we create systems that are way more flexible, way more adaptable, and frankly, just a lot more useful in the messy real world.
So let's just do a quick recap. The big idea is that AI uses probability to think when it doesn't have all the facts. We saw how Bayesian networks give it a visual map for all those complex cause and effect chains. This setup lets the AI update its beliefs on the fly as new info comes in. And best of all, this isn't science fiction. We just saw the Python code to make it happen right now.
And I think this quote just nails it. The whole point of this kind of AI isn't to find some perfect, absolute truth, because that almost never exists. The goal is to build systems that can make the absolute best, most rational decisions possible with the messy, incomplete information they actually have. So, I'll leave you with this thought. As this technology gets more and more powerful, it's going to be able to untangle incredibly complex webs of maybes. So what's the one big uncertainty out there, maybe in science, in your business, or even just in your day-to-day life, that you would want an AI like this to tackle first?